No. Morning. Answer in a bit. Next, listen to this first.
And then anytime I can write it from the
So, we're going to talk about power. Hey, what's up, everybody? Power doesn't involve, that much in terms of, talking about this. So, and typically the way I talk about power is I got a water bottle, right? And so I'm going to lift up this water bottle two different ways. You tell me which way I exerted more power, okay? So, wow, that's one way. Here's the second way.
Oh my God, aggressive punch.
Which one did I exert more power?
Second one.
The second time. What about the work I did, or the change in energy?
Oh, it's the same.
The change in energy is the same, and that's the thing with energy that makes it very nice and convenient. It doesn't care about, and then why? How do you know I exerted more power the second time?
In a short period of time.
So there's there was a big cell, but that was beside. But what is it? Shorter period of time, right? So the same work was done. The change in energy, right? Work is the change in energy of the system. The change in energy was the same, but it happened over a smaller period of time. And that is essentially what power is. Power is the rate of change of energy.
Slope of this.
I can do it.
So if now in this case, I could also do more energy in a certain amount of time. That would give me more power as well. But in this case, the work done, or the energy change, was the same, and I did it in less time. So if the change in energy is the same and I do it in a small amount of time, I'm going to get more power. Not to be confused with pressure, even though they're both capital P. So now if we have if that's the instantaneous rate of change of power. So if power is fluctuating, you might sometimes see that in like a generator or something like that where power fluctuates. You can always find out what the power is at any moment for doing the it's the derivative of the energy with respect to time. So work does not. That's what makes work and energy so nice and convenient. Is it doesn't care. It doesn't give a crap about time, right? The amount of time it took to get here and the amount of time it took to get here, the change in energy is the same. And that's what makes things like, the box going down the ramp and doing all that other type of things. We couldn't solve that with forces and kinematics and stuff like that, but we always had to split up those things, tilt our axes, and do all this crazy stuff. With work, it's what's the initial energy, or energy, what's the initial energy, what's the final energy, are there any non-conservative forces doing work, great, done. You can, with power though, is putting back that time idea in, is putting that time idea back into the equation. So, okay, the energy change or the work done is the same, but what was the rate at which you did it? That's what power is all about. So now, if you don't really care about instantaneous power, you can say, you can find the average power, and the average power would just be the change in energy over the change in time. Both of these are fun. It just depends on what you're looking for. So sometimes it's going to ask you what's the average power, what's the power exerted over, from 0 seconds to 15 seconds or something like that. In that case, you can just use the change in energy or change time. But if they're asking you for the instantaneous power in any specific minute, well then you're going to probably want to do a derivative or something along those lines. Another thing we can look at is that we know what's the relationship between work and energy? Work is equal to the change in energy, right? It's how the energy changes. Work does not equal energy. Work equals the change in energy. Remember, work can put energy into a system or take energy out of a system. And if we know that work is equal to the change in energy, well then I could always just replace this with, this is the same thing as saying it's the work done divided by the change in time. So it's either the change in energy of a system over the change in time, or the work done by an external force over the change in time. And yeah. Both these ways are totally legit to write it this way. There's nothing wrong. And it just depends on what you're given. If you know like how much force is being applied to an object and how far it went, well, you could use work, right? But if you know instead, like, the change in kinetic energy, you know how the velocity changed, and you know how the height changed or something like that, oh, that's the change in energy, that's going to be easier to use that equation. Depending on, what you want to do, it's fine. In fact, while this is work's relationship to energy, what is the mathematical definition of work? Force times the displacement times cosine theta. I'm going to make the assumption that we got some force exerting this way, and that the displacement is this way as well. So what's cosine of theta going to be? Theta is going to be 0, but cosine of theta will be 1, right? So I'm making this assumption for this example I'm about to do. So, okay, I could then calculate the, let's say it's the average force, right? So if it's the average force over some distance, then I could use this, the power would be equal to the work done over the change in time, or the power, that'd be the average power, would be equal to the average force multiplied by the displacement over the change in time, right? Plugging in work into as a force over a distance. Cosine of theta is 1, so I'm not writing it down. And hey, what the devil is this?
That's wait.
Velocity.
Wait.
That is the
Velocity.
average velocity. Yes. The change in position over the change in time is one of the first things you learn in this class.
I don't know about that.
Kinematics. What a joke.
Is that a crime?
So the average power then is just going to be the average force multiplied by the average velocity. That's another thing that you can use to I don't know if that's on your equation sheet, but you can, I mean, as you can see, it's easily derivable.
Easily.
Well, yeah, work it,
Just need to know. Yeah. What's velocity?
Power change. Oh, they do give it to you.
Oh, thank God.
Except they give it to you as a dot product.
That's not good.
So on your equation sheet, they just say, this they're doing the, you can do instantaneous power as well. That'd be the instantaneous force, not the instantaneous velocity. So that's the way they're doing it.
Multiply that x.
Wow, that's so weird they give you that. That's, whatever. Yeah, power. This is kind of the like official definition, but you can also calculate it this way if you know the force and the velocity. And on your homework, you kind of need to use all this stuff. So yeah, that's yeah, pretty cool. Oh, I wanted to bring up one other thing. Sometimes they'll give you the power and then say, what is the change in energy? Well, in that case, I can use, this is what we call the integral form of power. Is that, so basically if I took dt and threw it over here, that would be then the change in energy is going to be the integral of the power dt. from some initial energy to some final energy. So it's the integral right there. You're having trouble with that? Calculus and Physics, Saturday Academy, 11th. See you then.
See you there. Everyone just comes. Oh my god. Everyone just crowded in.
One more thing. What's the units? What's the unit of power?
Power over time, so it would be
So-
joules over time.
Joules per
Second.
second, right? Joules per second. But nobody says joules per second. What do we say instead?
We say
Watt?
What?
Watt? So the units are watts. That's a joule per second. It's the same thing. We just say watts. So anybody who's ever seen their energy bill, they know it's in kilowatt hours, right? So
Meters per second.
watt, a watt multiplied by time. Oh, that's energy. So that's the amount of, and a kilowatt hour is the amount of energy you consume. So if I took the power multiplied by the time, that would be a kilowatt hour. And that gives you your change in energy. And the energy you use. Yeah. Or where do you guys see watts a lot in just everyday? Light bulbs, yeah, right? So which one is a brighter light bulb? Is it going to be the 100-watt light bulb or the 60-watt light bulb? The 100-watt light bulb, yeah. The bigger the wattage, the bigger the more bright the bulb tends to be. Yeah. So yeah, question, and that basically just means that that particular light bulb uses more energy over per moment in time, and that's why it's brighter. It illuminates more. Questions, comments, concerns so far? So what you guys are gonna do, you're still free to finish up any labs you have to do. So there's the pendulum lab over there. I got the poppers back there. I got the poppers back there. But the last part of your lab that you're going to do is a power lab. Yes.
Oh, is this with the fans?
You sound so disappointed.
No, I was asking.
Retarded fan. Michael's disappointed.
No, it was fun watching it, but it seemed like very hard when they were trying to solve stuff. So.
Oh no, not difficulty. Not an AP class. So you're going to be essentially making one of these. This you'll be working with a partner. So it's just 2 people per, and each partner, each pair, I'm giving 8 skewer sticks and 8 paper plates, and that's it. You're also free to scrounge through the scraps that are over there. They're only in the box, nothing else. So only in the box. And then corks are over there as well. You're free to take whichever cork you want. But yeah, you're going to design some sort of thing. This one was designed by Edward last year.
Yes.
So, and then basically each one has been drilled with a hole inside of it. It's supposed to fit snugly, so if you're having trouble, that's good. It fits snugly in there like that. And then there's a cup here. You can put in however much mass you want. Like that. And then, so you guys have seen turbines before, right? They rely on the fact that the sun naturally makes a temperature gradient that then causes hot air and cold air to move, and that causes the wind, right? And the wind is consistent in some areas, so if you put something like a turbine in front of there, that wind can be used to do useful work. So work is being done on the system by the wind.
Wow, Edward. Cool design.
10 out of 10.
And so what you guys are going to do is you are going to basically you got till the end of the period, but you're going to design a turbine blades such that you want to generate the most power that you can, and then you're going to calculate the power that you produce. Because right, this thing's doing work, so you should be able to figure out what measurements you need to make to calculate that power. Because I got work being done, and it changes what?
What?
It's changing the energy into
Potential.
gravitational potential energy. Yeah.
Let's get started.
Yeah.
Questions on what you're doing? So once you got a partner, come on up here. You can get your plates and skewer sticks. Remember, 8 only.
That's
Oh, I'm sorry.